Decoding efficiency. Mastering algorithm design. In modern programming, coding algorithms form the backbone of software development, yet they remain one of the most misunderstood aspects of computer science. Whether you're building a mobile app, optimizing a machine learning model, or managing vast datasets, the choice of algorithm can determine success or failure. This guide delves deep into the world of algorithm design, exploring its nuances, challenges, and best practices. The art of crafting efficient algorithms requires both theoretical insight and practical experience. From sorting arrays to solving graph traversal problems, every decision carries weight. Understanding the underlying principles helps programmers write cleaner, faster, and more scalable code, a skill that sets exceptional developers apart from the rest. Understanding algorithms. Beyond textbook definitions, an algorithm is a precise set of instructions designed to solve a specific problem or perform a particular task. It's not merely a series of lines in a program, but a structured approach to transforming input into output efficiently. At its core, algorithm design involves identifying patterns, decomposing problems, and implementing solutions in a way that minimizes computational overhead. Algorithms operate on the principle of step-by-step execution, ensuring predictable results regardless of input size. However, efficiency varies greatly depending on factors like data structures used, loop iterations, and branching logic. A poorly optimized algorithm might function adequately for small inputs but fail catastrophically at scale. Time complexity measures how long an algorithm takes to run relative to input size, typically expressed using big O notation. Space complexity evaluates memory consumption during execution, crucial for resource-constrained environments. Choosing the right algorithm hinges on analyzing these metrics against problem constraints. For instance, a brute force method may suffice for simple tasks but becomes impractical when dealing with millions of records. Recognizing this balance is essential for any developer aiming to build robust systems. In modern programming, algorithms aren't isolated entities. They interact with other components like databases, APIs, and UI layers. A well-designed algorithm ensures seamless integration without creating unnecessary bottlenecks elsewhere in the system architecture. The importance of selecting the right algorithm. Selecting an optimal algorithm begins with clearly defining the problem domain. Is speed critical? Does memory usage matter more? Are there constraints on hardware resources? Answering these questions narrows down viable options significantly. Without clarity, even brilliant minds struggle to produce effective solutions. Consider a scenario involving frequent searches over large unsorted collections. Implementing a naive linear search would work initially but degrade rapidly as dataset sizes grow. Replacing it with a hash table-based solution drastically improves lookup times, from O(n) to O(1), demonstrating why careful selection matters so much. Real-world implications of poor choices. A study by Google engineers revealed that inefficient algorithms cost organizations billions annually due to excessive compute costs and slow response times. In e-commerce contexts alone, suboptimal recommendation engines lose out on significant revenue opportunities by failing to deliver personalized experiences quickly enough. Maintaining legacy codebases further emphasizes the need for strategic algorithmic decisions. Refactoring outdated implementations isn't always feasible. Sometimes improving surrounding infrastructure offers better ROI than rewriting everything from scratch. Learning strategies for mastering algorithms. Becoming proficient in algorithm design demands deliberate practice. Online platforms like LeetCode offer curated problem sets ranging from beginner-friendly exercises to mind-bending puzzles. Engaging regularly with diverse challenges sharpens analytical skills and exposes learners to various paradigms including recursion, divide and conquer, and backtracking. Reading seminal works such as Introduction to Algorithms provides foundational knowledge covering classic data structures and fundamental algorithmic concepts. These books go beyond surface-level discussions into mathematical proofs behind popular techniques, helping readers understand why certain methods work better than others mathematically. Collaboration plays a vital role too. Participating in hackathons or coding groups allows sharing ideas, discussing edge cases, and gaining fresh perspectives on familiar topics. Teaching someone else reinforces comprehension levels far more effectively than passive reading ever could. Practice doesn't mean mindless repetition either. Focusing on understanding core principles instead of memorizing solutions leads to deeper retention and adaptability. When faced with novel situations requiring creative adaptation, strong fundamentals shine brightest. Optimization techniques, greedy approaches versus dynamic programming. Two widely used optimization strategies stand out: greedy algorithms and dynamic programming. While both aim to find optimal solutions efficiently, their application depends heavily on problem characteristics. Greedy methods make locally optimal choices, hoping they result in globally optimal outcomes. Dynamic programming excels at problems exhibiting overlapping subproblems and optimal substructure properties. By storing intermediate results, it avoids redundant computations, saving substantial processing power, especially when applied recursively multiple times. Let's examine an illustrative case, the knapsack problem. Here, we must select items maximizing value without exceeding capacity limits. A brute force solution enumerates all subsets, which grows exponentially, making it impractical for larger instances. Applying dynamic programming transforms this challenge into manageable chunks. We construct tables tracking maximum values achievable considering varying capacities and item combinations, progressively building toward final answers systematically. Conversely, greedy approaches excel in situations where local optimality guarantees global optimum. Huffman coding serves as perfect example, compressing data effectively via frequency analysis, prioritizing frequently occurring symbols. However, relying solely on greedy strategies risks missing true optima, since locally best choices don't necessarily yield globally ideal states. Knowing when each technique applies prevents costly mistakes later during implementation stages. Debugging complex algorithms, common pitfalls and solutions. Even experienced developers occasionally encounter bugs creeping into intricate algorithm implementations. One prevalent issue stems from misunderstanding asymptotic behavior assumptions, leading to unexpected runtime discrepancies, particularly noticeable only after scaling up test cases. Off-by-one errors represent another frequent source of frustration, especially in loops iterating through arrays or strings. Properly initializing counters along with rigorous boundary condition checks mitigates many related issues early on, preventing cascading failures downstream. Recursive implementations introduce additional complexities, primarily concerning stack overflow risks associated with deep call stacks. Setting reasonable recursion depth thresholds coupled with iterative alternatives proves beneficial whenever possible, reducing dependency on potentially unstable mechanisms. Unit tests play indispensable roles, verifying correctness under varied scenarios. Writing targeted assertions validating outputs against expected results catches subtle regressions, promptly facilitating swift resolution cycles, minimizing production downtime. Visualizations aid immensely in comprehending algorithm flows, visually depicting state transitions, enabling easier identification of logical inconsistencies. Tools capable of animating execution sequences provide invaluable insights otherwise difficult to grasp. Purely analytically. Evolving trends shaping future algorithm development. The field continues evolving rapidly, driven largely by advancements in artificial intelligence research areas focusing increasingly towards neural network architectures mimicking human cognitive abilities previously unimaginable through traditional means. Quantum computing introduces revolutionary possibilities, redefining encryption standards, challenging classical cryptographic protocols relied upon securing digital communications worldwide. Researchers actively explore post-quantum cryptography alternatives, preparing society ahead of anticipated disruptions. Data privacy regulations impose stricter requirements, necessitating innovative anonymization techniques, preserving utility without compromising confidentiality. Differential privacy emerges as promising framework, balancing transparency demands with individual protections, ensuring ethical data handling across industries. Federated learning represents paradigm shift, allowing collaborative training without centralized storage, eliminating single points of failure, enhancing security, simultaneously protecting sensitive information residing locally on devices, rather than aggregating centrally. These innovations underscore necessity staying abreast latest developments, continuously updating expertise portfolios, maintaining relevance amidst ever-changing technological landscape. Mastering advanced topics through practical application. Advanced algorithmic concepts require hands-on experimentation to truly grasp. Exploring parallelism opens avenues, leveraging multi-core processors, distributing workload efficiently, accelerating execution speeds substantially compared sequential counterparts. Graph theory constitutes rich area, offering multitude applications spanning social networks, mapping relationships, identifying shortest paths, locating clusters, detecting anomalies, pinpointing influential nodes, among countless other uses. Machine learning integration blurs boundaries between statistical modeling and deterministic computation. Hybrid models combine rule-based heuristics with probabilistic reasoning, producing adaptive systems responsive to environmental changes, dynamically adjusting behaviors accordingly. Cloud-native deployment shifts focus towards serverless architectures, abstracting infrastructure management, letting developers concentrate exclusively business logic implementation, increasing agility, decreasing operational overhead dramatically. Containerization enables consistent environments across development, staging, production phases, ensuring reliability irrespective of physical locations, simplifying maintenance operations, streamlining continuous delivery pipelines, fostering innovation cultures, promoting rapid iteration cycles. Building scalable systems with algorithmic awareness, designing scalable architectures mandates foresight, anticipating growth trajectories, selecting appropriately suited algorithms, avoiding premature optimizations that hinder flexibility down road. Premature optimization, famously warned against by Donald Knuth, highlights dangers over-engineering initial versions, sacrificing simplicity, extensibility unnecessarily. Microservices decomposition facilitates independent scalability, dimensions isolating functional units, permitting separate scaling according to demand profiles, decoupling interdependencies, reducing coupling, enhancing modularity, supporting agile development methodologies, effortlessly adapting changing market dynamics. Load balancing distributes traffic intelligently, directing requests toward least busy servers, ensuring high availability, minimizing latency, improving user satisfaction, retaining customers, increasing engagement metrics, positively impacting bottom line figures. Caching strategies reduce database query load by temporarily storing frequently accessed data, serving subsequent identical queries, instantly bypassing disk I/O operations, conserving bandwidth, prolonging device lifespans, lowering operational expenses, achieving triple benefits concurrently. Monitoring. Dashboards visualize system health indicators, alerting teams proactively before incidents escalate, empowering timely interventions, averting downtimes, maintaining service level agreements, fulfilling contractual obligations, ensuring customer trust, loyalty, strengthening brand reputation organically. Conclusion. Coding algorithms lie at heart of successful software development, influencing everything from responsiveness to reliability. Mastering them entails blending theoretical rigor with pragmatic application, navigating intricacies, inherent complex problem spaces, confidently devising elegant solutions, addressing real-world challenges creatively. To thrive in competitive industry landscape, invest consistently, honing algorithmic proficiency, embracing lifelong learning journey, engaging vibrant communities, exchanging knowledge, pursuing excellence, relentlessly pushing boundaries, discovering new horizons, expanding capabilities infinitely, growing professionally, personally, enriching lives profoundly, impactfully.